before I start talking about Unit 7, was just going to briefly talk about the Unit 6 tests. So overall, they were pretty good. Like most people did fairly well on them. I did just finish grading them literally during like my lunch. So if you haven't looked at your grade, it is an Infinite Campus at this point. Definitely like feel free to double check me. I haven't had a chance to upload the answer keys just because again, I did just finish grading them. But definitely feel free to kind of look at Infinite Campus, just make sure like if you thought you did off your briefcase binder, but you didn't get 100, maybe just make sure it all synced up and things like that. If you made below 79, then obviously you'll have options to do recovery. I'll give recovery tests the next few Wednesdays, or if you're just planning on doing the corrections, then I'll take those up until your Unit 7 test, which is going to be on March the 10th. Other than that, like today we are going to go ahead and start Unit 7. I did want to kind of set up Unit 7 for you. So this is one of the units that many students do find to be one of the more challenging ones that we have this year. Just to go ahead and get that out of the way, most students do find this one to be a little bit of the more challenging one. I think it is challenging because it does involve applications of integrals. There's going to be a lot of theorems, there's still going to be some new formulas, and it is a whole lot of word problems. Even for some of the problems, we're going to do some things like actually like explaining our answer and like writing out sentences, which we don't often do a lot in calculus, so like it is kind of a very different type of unit. That being said, I think it's a very, very important unit. Like I can almost guarantee you on your AP exam, the AP exam has 6 free response questions. And those free response questions are 50% of your overall score for like the 1 through 5. I can pretty much guarantee that there's going to be 2 free response questions that come directly from this unit, if not 3. So I like to tell students, like, if you can do this unit, and if you get this unit down, like, super, super well, I can pretty much guarantee you a 3 on the AP exam. But you have to get this unit down because it is a heavy portion of the free response section of the AP exam. So how I have it set up, before the quiz, we have 2 topics. We have the second FTC, which is going to be more like an algebraic and kind of looking at graphs. It's like the easier of the 2 topics we have. The second part before the quiz, and this is kind of where I just want to give you a heads up, it's going to be the applications of the first FTC. If you had a chance to look at the homework, homework 2 is definitely the longest homework you have seen from me and will see from me. It is long homework, only because there's just like a lot of different things you have to practice. And so I am just going to say like a heads up, if you're the type of person who likes to procrastinate, like don't procrastinate on homework 2, or like you're just never going to catch up. Like it's just one of those things, like if you miss it, like you're just not going to be able to dig yourself out of that hole because it just has like a lot going on. So that's just my warning this unit. Like just don't procrastinate. As long as you kind of keep up, you'll be fine. Like it's not impossible, but it does get really difficult if you allow yourself to fall behind. So today we are going to be looking at the second fundamental theorem of calculus. And so when we're talking about the second fundamental theorem of calculus, really before I can talk about it, I do want to talk about a thing called an integral defined function, because we're going to be seeing a whole lot of these in this unit. So in math, you've been dealing with functions pretty much like always in math. Like you have f of x is sine of x. You have g of x to be x squared minus 2. Like you know what a function is. You've been doing them forever. We're now introducing, if you will, like a new family of functions. And this new family of function is going to be an integral defined function, which is what you see this g of x is. So let's talk about kind of what it looks like. I do think it looks weird when you're first kind of seeing it for the first time. We have g of x, and g of x is equal to the integral from 2 to x of 3t squared dt. So the function g of x is literally an integral, and it is the integral of 3t squared. We use a t right there just to kind of keep it separated from the x, because this is a function of x, and we just don't want to kind of mix up the variables. Before we get too much into it, let's just kind of think about how I would evaluate it. So like on that first line, I have find g of 3. Well, if this was just a regular function, what does g of 3 mean? How would you find g of 3? just plug in 3 for x. We know how function notation works. This one is just now an integral, so what is g of 3? Plugging in 3 for x, it literally turns into the integral from 2 to 3. So what is g of 3? I've replaced the x with a 3, and then this is now just like a regular definite integral defined. What's the antiderivative of 3t squared? Add 1 to the exponent, divide by the new exponent, so it gives you t cubed. Plug in the top, minus plugging in the bottom. I get 3 cubed minus 2 cubed. Could simplify it, but I'm lazy. I'm going to leave it like that. These are sometimes called an accumulation function. Because if you think about it, it's kind of like they're accumulating areas. So like if I want to interpret this function, g of 3 is literally how much area has accumulated from 2 to 3 under the graph of 3t squared. Where we'll eventually go into this is maybe 3t squared represents the amount of snow falling in a city, or maybe the amount of fish swimming in a lake, or the number of people getting on an escalator, or any type of word problem that we'll create, and we'll have to interpret it in like a verbal context as well. But for now and today, we're just going to be talking about these integral defined functions without like all the word problems. So we'll go ahead and try those bottom two for me. So same function, I want you to find g of 2, which honestly should be a little bit easier, and then I want you to also go ahead and find g of 1. And again, we're not going to overcomplicate it. When we see g of 2, just regular function notation, that means, hey, every time you see an x, replace it with a 2. So go ahead and try those two for me. Yes. You're going to like close out the notebook and go back and reopen it for meetings. So g of 2 should be an easy one. Like you don't even have to find the antiderivative. So again, I'm replacing the x I had with a 2. Don't waste your time on this one. If you start at 2 and end at 2, how much area have you accumulated? 0. So no point in doing it. You could, but you're going to get 0. This one, it is going to end up being backwards, but again, we can still evaluate it the same way. So the antiderivative is t cubed from 2 to 1. Yes, it's backwards, but still plug in the top, minus plugging in the bottom. That's what? 1 minus 8, so negative 7. Or of course, you could leave it unsimplified. So those are what we call integral defined functions. Now let's talk about what we can do with them. G of x is a function. So literally anything you have ever done with a function, you can also do with an integral defined function. So I could find the x-intercepts. I could find the intervals of increasing and decreasing. I could find the relative minimums and the relative maximums. I could find the derivative of it. I can integrate it. I can find the second derivative of it. Anything you've ever done with a function, we can do with these integral defined functions. And that's kind of what we're going to focus on today. The main thing we're going to talk about today is how do we find the derivative of these kind of weird integral defined functions. That's kind of the whole point of this thing called the second fundamental theorem of calculus. I like showing students where it comes from, just because I think it makes memorizing the rule a little bit easier. So I'm going to do it the long way, and then we'll kind of look at some comparison and kind of see where it comes from. Normally, we wouldn't do all of these steps. But I chose that same one. We have g of x is equal to the integral from 2 to x of 3t squared dt. And we ultimately want to take that g of x and find g prime of x. Now, we don't know the shortcut yet, so we're going to do it the long way. Right now, we don't know how to take the derivative of an integral. But what we do know how to do is we do know how to rewrite g of x so that it no longer has an integral sign in the problem. Well, how can we rewrite g of x so there's no longer an integral sign in the problem? Let's just go ahead and evaluate it like a definite integral. So that's the integral of 3t squared. What's the antiderivative of that? T cubed. Still going to have to plug in the top number minus plugging in the bottom number. So plugging in the top gives us x cubed. Plugging in the bottom, 2 cubed, which is going to give us 8. What was the point of doing that? Yes, g of x is the integral from 2 to x of 3t squared, but g of x is also the same thing as x cubed minus 8. Why would we want to do that? Let's talk about the derivative. If you want to find g prime, which one is going to be the easier one to find? The integral or x cubed minus 8? Definitely the x cubed minus 8. And what's the derivative of x cubed minus 8? 3x squared. 8's a constant, so it's going to go to 0. Now what we want and kind of what we hope is there's a shortcut to go straight from the integral to its derivative. Anyone notice any patterns from that original integral to what its derivative is? You just replace the t with an x. So we saw this 3t squared, and its derivative became 3x squared. Let's think mathematically why that makes sense. Big idea. How would you describe the relationship between the integral and the derivative? What are they to each other? They're opposites, right? They're opposites, they're inverses. Well, in math, when we use opposites against each other, like when you take the square root of an x squared, or when you multiply by 4 when you're dividing by 4, what happens when you use opposites in math? They cancel each other out. So basically what's happening here, if I am taking the derivative of an integral, well, the derivative of an integral, it cancels out, leaving us just what's on the inside. Why does that t turn into an x? Could go about the long way about it, but basically what's happening is this is still a function g of x, so we still want it to be in terms of x, so that's why it becomes 3x squared instead of saying 3t squared. So we do want a shortcut. So the shortcut we're going to use is what I call the second FTC common case. And there's common for you. So what does the second FTC tells us? It tells us how to take the derivative of an integral. So we are taking the derivative of an integral. Mathematically, what that is going to happen is the derivative is going to cancel out the integral. If, and there's a big if of when that will happen, you have to have two things true for that derivative to completely cancel out the integral. The first thing that has to be true is the bottom number on your integral sign has to be just a number. So it could be 0, it could be 2, it could be -5, it could be 5,000. It has to be just a number. The top part of your integral sign has to be just x. Not x squared, not 2x, not sine of x, just x. And when we take the derivative of an integral, they basically cancel each other out, and we just have f of x. Basically, the t is replaced with an x. In words, if you're not kind of like the math person, we can just say basically replace the t with the x. And not going to worry about the quick proof because we did see an example of kind of why that worked on the previous slide. So that is the common case. And you can probably understand by the name common case that yes, this is what's going to most likely happen, but probably what is not always going to happen. So when we don't have the common case, we're going to use what I'm going to call the general case. Here's an integral defined function that is not so common. I do think this is a little bit scary when you first look at it. You're like, the g of x of, and this is the integral from 5x to tangent of x, of 3t squared dt. It looks weird, but it's just an integral. You can kind of imagine, like if I wanted to find g of like pi, you just replace the x's with pi, and that would turn into like numbers, and then it would just be a regular integral. That being said, it's a function. What do we want to do with functions? We want to be able to find the derivative of functions so that we can do some analysis of it. So eventually we want to be able to jump straight from, if I know what g of x is, I want to be able to jump straight to g prime. do like showing students kind of where this formula comes from first. I think it helps students memorize and see where it comes from. So if I wanted to rewrite g of x without the integral sign, 3t squared becomes t cubed. Plug in the top minus plugging in the bottom. So g of x is the same thing as tangent of x cubed minus 5x cubed. So that is what g of x is. Again, there's nothing new there. We just evaluated the antiderivative, plugged in the top, minus plugged in the bottom. And then we want to take the derivative of it. We do know that the derivative would cancel out the integral sign, but there's some other kind of funky stuff going on in this one. So I'm going to take the derivative of this rewritten version of it. What derivative rule I mainly need to be focused on when I take the derivative of that rewritten version of g of x? The chain rule, right? So g prime, let's do the chain rule. 3 comes down in front. The inside stays the same. The new exponent would be 2, and then times the chain rule. The derivative of the inside is secant squared of x. Minus, same thing. 3 comes down in front. New exponent is a 2. Inside stays the same, times the derivative of the inside, which is 5. Definitely a messier derivative, but I hope you can kind of still see some patterns. So the original integral was the integral of 3t squared. And you can kind of see that 3t squared showing up in the answer. So we have 3 something squared, 3 something squared. Instead of replacing the x with, the t with an x, we had to replace the t with something a little bit more. Where's this other part coming from? Well, we are still taking the derivative, so we still have to use the chain rule. That's kind of where that's coming from. To kind of formalize this and kind of put it as a formula, this is what I'm going to call the second FTC general form. So this is when you don't have a number on the bottom or an x up top. The formula is basically going to be plug in the top times the derivative of what you plugged in minus plugging in the bottom times the derivative of what you plugged in. Again, what's happening here mathematically? Let me be a little bit better with that. There is a dx in front of that because we are taking the derivative of an integral. Yes, the derivative is canceling out the integral, but because we have just more junk on the integral sign, we have to worry about like evaluating it correctly and then doing the chain rule. For those of you who think that formula looks confusing, if I were to put it in words, again, it's basically going to be plug in the top times its derivative minus, because we are still evaluating an integral in some ways, plugging in the bottom times its derivative. And so that is the general form. So we have the common form, which honestly probably shows up about 70% of the time. And then the general form, not as common, hence its name, but is something that we still definitely need to know how to use and kind of recognize. Now, some people are like, Mr. Brown, I am already memorizing enough of this class. Can we just memorize one of them and be done with it? And like, the short answer is yes. You can just use the general case every single time you get the right answer. But just being familiar with the common case will just save you a little bit of time. The reason why it works, so again, this is just kind of for those of you who just like want to use it. You can use the common and general case every time. So yes, there's common and general. Using the common case, so like a is a constant, this is just x. Normally the derivative would just become f of x. That's how I would recommend doing it, just doing the common case. If you just want to memorize one formula, always do the general case. So you would basically have to say like, okay, plug in the top times the derivative of what you plugged in. The derivative of x is 1 minus plugging in the bottom. A is just a number, so times the derivative of what you plugged in, which would be 0. So like you're still going to get f of x, just take you a little bit longer to get there. So again, why are we doing this? Like today we're mainly going to focus on just like finding these derivatives. But again, anything you have ever done with a derivative, you can do with these integral defined functions. You can write tangent lines, intervals of increasing and decreasing, all those same things we can do. Let's go ahead and just practice using these rules. So I have 3 of them. We'll start with these 2. So again, I have the derivative of an integral defined function. So you can kind of think of this as we are taking the derivative of some integral defined function. Looking at this first one, this is the integral from 4 to x. Can we use the common case? Yeah. Yes, we have just a number on the bottom, just an x up top. Not going to make these more complicated than we need to. If you have the common case, what's the only thing you need to do? Replace the t with the x. Just plug it in. Again, why we do that, the derivative cancels out the simple integral. This one is just going to be the square root of x. Easy enough. Could do it the general one if you just like doing it the long way. If you're using the general case, plug in the top times its derivative minus plugging in the bottom times its derivative. Simplifying that, you're still going to get the square root of x. Looking at that second one, can we use the common case for that one? Definitely not. There's a whole lot of stuff going on. So we are going to use the general one. I know I don't have t's there, but we'll just treat theta kind of the same way. So using this one, I am going to plug in the top. So this is going to become the secant of the natural log of x times the tangent of the natural log of x, plugged in the top, times the derivative of what I plugged in. The derivative of the natural log of x is 1 over x. Minus, plug in the bottom, so that will become the secant of x squared, tangent of x squared, times the derivative of what we plugged in. What's the derivative of x squared? 2x. Now that's an ugly derivative. I wouldn't ask you to do like integrals of increasing and decreasing with that mess, but that would be the derivative we would use. Try that last one on your own for me, and then we'll look at an example of actually using this to solve a problem. I got just 2 or 3 more slides of notes, and then we're going to stop for today. And as you're looking at this one, so we're taking the derivative of an integral defined function. Normally, a derivative could cancel out an integral if we have the common case. If we don't, then we have to kind of do a little bit more work to kind of get to our answer. Can we do the common case for this one? No. Like, yes, there is a number on the bottom, but it's not just x up at the top. I'm not going to overcomplicate it. We're going to just plug in the top times the derivative of what you just plugged in. So times 2x, minus plugging in the bottom, times the derivative of what you just plugged in. And be careful with constants, because the derivative of a constant is 0. Don't have to simplify it, but pretty easy to see that this last term is just going to become 0. So let's look at one example. Again, I could be up here all day long just looking at example after example of using these. Let's do one that I think most people are pretty familiar with, and that's going to be a tangent line. So I have, for the given function g of x, this is that same as that first one we did on the previous slide. It says find the line tangent to the graph at x equals 4. So again, first semester topic, we reviewed it some on the homework 0 from last unit. Let's review tangent line. To do a tangent line, the format we use, y minus y1 is equal to m times x minus x1. That's a tangent line. To write a tangent line, you need 2 things. You have to have a point, and that point's going to be x1 comma y1. And then you also have to have a slope. Where does that slope come from? That slope is going to come from the derivative, of course, because we're in a calculus class. So let's write the line tangent to this graph. And I do want to be clear what we're writing the line tangent to. There's this function g, which is representing the accumulating area of the integral from 2 to x of the square root of t. I want to write the tangent line to that kind of function, which we have no idea what it looks like, but we want to write the line tangent to it. Doesn't matter which one you find first. You can find the point first or the slope first. I'm going to find the point first. I know if I'm looking for this point, we do need to have the x-coordinate and the y-coordinate. I know the x-coordinate is 4. In math, how do I find the y-coordinate that goes with a particular x-coordinate? Plug it into the original equation. What is the original equation? The original equation is g of x, so I do want to find g of 4. Well, what is g of 4? That would be the integral from 4 to 4 of root t dt. If that was a harder one, you have to find like the antiderivative, plug in the top minus the bottom. Show this one for the sake of time because it's easy, because what is that integral going to be equal to? 0. Start at 4, end at 4. We have no area. I know that integral is 0. So there's the point. Then after we find the point, we do want to make sure we also have the slope. Well, in order to find the slope, we have to have the derivative. Here's where the second FTC is going to come into play. Already did this one, but are we using the common case or the general case for this one? Common case. Bottom number's a 4, top number's just an x. So g prime is literally just the square root of x. I want to find the slope at 4. The slope at 4 would be the same thing as root 4 or 2. Now I have all my information and I can write my tangent line. So I have y minus the y-coordinate is equal to the slope times x minus the x-coordinate. I'm fine if you leave your answer like that, or you can also simplify it into any equivalent answer. Again, that's just one example. The homework has some more, like there's some that make you do intervals of increasing and decreasing, some that make you go back and find like the second derivative, but like anything you've done with the function, you can do with these integral defined functions. So that's like the first half of these notes. This is what I call like the analytic examples, the one where you're doing it all algebraically with like the functions and the numbers. Any questions on anything I've done so far? All right, so then the second half, which we're mainly going to finish tomorrow, but I did want to start it today. And that's going to be the graphical examples. Probably can guarantee you one of your free response questions on the AP exam will be a problem that looks just like this. They'll give you some weird looking graph. They will also give you some integral defined function. So let's like talk about what we have, and then we're probably gonna do at least this slide today, maybe the second one, depending on the time. So they give me the function g of x, and g of x is basically what we're going to be answering a lot of questions of. So we could ask you things like, when is g of x increasing? Or like, what's the maximum of g? When is g of x concave up? But we have to kind of look at g of x. G of x is defined as the integral of f of t, and that is the graph that we're looking at. So we're not looking at the graph of g. We're looking at the graph of f, where g is the integral of f. Also, a big thing you want to do at these is you always want to look to kind of see where that integral is starting at. Don't assume that it's starting at 0. For example, this one is starting at 1. So for all these problems, like 1 is kind of going to be like our starting point. So let's just do the basic ones first. This is just going to be us evaluating the function. Also some good review, honestly, of some topics from Unit 5. So I have 3 values that we want to find. I want to find g of 3, g of 1, and g of 0. So again, let's talk about what this means. If I want to find g of 3, that literally means, hey, replace the x you see with a 3. So g of 3 would be the same thing as saying the integral from 1 to 3 of f of t dt. And again, I just replaced the 3 with the x, or the x with the 3, I should say. Do we have enough information to find the integral from 1 to 3 of f of t? Yeah, you have the graph. What do we know the definite integral represents? the area, right? So we're starting at 1, ending at 3. Just divide it up into some shapes and find the area. So I see a square, a rectangle, and a triangle. Square has an area of 4, 2, 1/2 base times height, 1. What is g of 3? G of 3 is how much area has accumulated from 1 to 3. Well, how much area has accumulated? 4 plus 2 plus 1 gives me 7. I know that area is positive because I am above the x-axis and moving forward from 1 to 3.
Minus g of 6.
I think you're on the next slide. Move up 1. There you go. So let's go ahead and kind of keep going. G of 1, what would that mean? That would just be the integral from 1 to 1. So again, that's why we always want to pay attention to what we're starting at. G of 1 will be the integral from 1 to 1 of f of t dt. Easy one. If you start at 1 and end at 1, how much area have you accumulated? 0. Those are ones you like. That would be 0. And then we also have g of 0. What will be g of 0? Still starting at 1, ending at 0 of f of t dt. What's the first thing you notice about the numbers on that integral sign? They're backwards. So remember that when it is backwards, you are going to have to use the opposite sign. So area that looks positive is actually negative. Area that looks negative is actually positive. So from 1 to 0, that's a triangle, 1/2 base times height. That is above the x-axis and positive 1. But since I'm moving backwards, it would have a net area of -1. Questions on those three? Yes, Mitch?
So you said at the beginning that it goes from x to 1 and not x to 0.
Mm-hmm.
So the bottom is 1, right?
Yeah, so like when I say starting point, so like that 1 was built into the function. So for all of them, no matter what integral we found, we're basically starting at 1 no matter what.
Okay.
And that's why looking at C, we were technically moving backwards because we're going from 1 backwards to 0.
So whatever that is, that's the starting point?
Yes, the bottom number will be like the starting point of all the areas.
Okay.
Go ahead and try 2A for me. Don't worry about B and C yet. Same graph, but I want you to find G of 6. And this is the slide we're going to stop at today. So we're finding G of 6. That's basically going to be the integral from 1 to 6. Again, that's not changing. We're just replacing the x with c with a 6. So again, we're still starting at 1. Now we're stopping at 6. I already found this area. From 1 to 3 was 7. So now I have another triangle, 1/2 base times height, 1/2 times 1 times 2. That gives me an area of 2. And then I have another triangle and a rectangle. It's below the axis, so it would be negative because we're still moving forwards. So what would be the area? G of 6 is basically going to be that 7 plus 2, which is 9. And then we're subtracting 3 from that, which is going to give us a net area of 6. Questions on where that value came from? All right, so here is where the calculus is going to come into play. That's going to be what we're looking at for G prime of 6 and G double prime of 6. So again, let's kind of think about conceptually what's happening. B is asking me to find G prime of 6. This is the graph of F. We have no idea what G looks like, but we do know this is the equation for G of X. if g of x is equal to the integral from 1 to x of f of t, do we now know how to find an expression for g prime of x? We do. We're taking the derivative of an integral. Can I use the common case or do I need to use the general one? The common one, because it's a number to x. What does the common case tell us? Just to replace the t with an x. So what is g prime of x equal to? G prime of x is equal to just f of x. And again, that came from the common case. So when I say find g prime of 6, what's an equivalent statement of saying g prime of 6? F of 6. Well, you've been in the 6th grade math class. Do we know how to find f of 6? We do. F of 6 is there. What is f of 6 equal to? -2. Think about how we can kind of expand this. We actually now have enough information to write the tangent line at x is equal to 6. So I have the point 6, 6 from part A, and I also now have a slope. So we can find lots of different information from the stuff that we have. Let's keep going though. And part C is asking us to find g double prime of 6. Let's just kind of keep going. If g prime of x is f of x, what do you think g double prime of x is going to be equal to? F prime of x. So again, if I say what's g double prime of 6, g double prime of 6 is the same thing as saying f prime of 6. What do we know the derivative represents in calculus?
Slope.
The slope. What is the slope at 6? 0. That's a horizontal line, so it has a slope of 0. I'm gonna stop there for today before we get to like the analysis and kind of like the writing sentences part. We'll start like interpreting parts of this graph. So I am gonna kind of stop class here. Also just have you time to kind of just absorb and think about this. The assignment that I'm officially giving you is homework 1. There is another homework 0, but it's not due until the day of the test. It is a very short one, so you can probably knock it out pretty easily. We are going to finish the notes tomorrow for the second FDC. So on this homework, I would probably recommend you only do the first half of it, the algebraic part, and save like the graph ones for tomorrow. There's still a lot more that we want to look at. So that's where we're going to stop at today. We'll finish these notes up tomorrow. If you're at home, then I will definitely see you tomorrow in class, of course. But definitely hang back if you have any questions that you wanted to ask or get clarified. Sometime after school today, I'll scan in the answer keys to the test so you can kind of compare it to yours. But until I get that, then yeah. I will pass out the test. I can pass them out today if you're in person. If you're at home, then you can obviously see your test already because it's virtual. If you're here in person, I'll go ahead and give you your test. Just know that I haven't posted the answer key yet online. But see y'all tomorrow.
Mr. Brown.
Yes.
So it says the Unit 7 test is on Friday the 3 to 10th.
Mm-hmm.
The Friday is the 12th.
Oh, cool. Because it's a Wednesday.
On Wednesday?
Yeah. It's another short test.
Are the rest of the tests that you're gonna be on?
Just depends on how the days work out. Like, I would rather not test on Wednesday, but
That's 3 tests in a row on Wednesday.
these are some short units. Like, first unit was like the long, drawn-out ones. This semester is like bam, bam, bam. Yeah. Like, this was like, Unit 8 is going to be real short. Like, you pretty much start Unit 8 and then it's like end.
Do we have 9 units?
And then we stop.
So is, for all this, so it says that find the first and second, but by giving us the first, right?
Well, you find the first with the second FDC, right? Like, that's the first derivative. The second would just be using a regular derivative. Right? So just be like cosine 5x.
Oh, I see, I was, okay.
It's like only the first derivative use like the new stuff.
5 times. No. Does this still work if the X and variable?
You would need to do the general one. Or just know it's gonna be a common one that you're gonna have to. Did that work?
It's still working, it's very long.
Oh, you added. First of all, that's two. What's the difference between what's not available?
If it's not available, it means to sync on another device. I never had that.
What's the word pilot? Maybe you have called it. So it's a little close off, so they lost some carry.
It did. And it did.
Yeah.
She had her hand up first and I was on her.
What do you do when you're backwards?
Just do the general piece.
Okay,
Or no, it's gonna be the negative version of the quantity.
okay.
I'm confused. So is this actually just f of x?
This is f of x. That's f prime. That's f.
But then I look at the notes and we're saying that g of x is that.
So those mean the same thing.
Yeah.
We're never gonna do this middle step anymore. We're always gonna jump straight from g of x to g prime.
But isn't this the same thing?
Those
Like
are
I'm
the
writing
same.
that as g of prime on these.
So you're doing, if you write this along with that, will become like 1/5 cosine of 5t plugging x minus 34. You're not.
And then is this right?
Common case, actually, I think, what's the majority of those words? Maybe like time, X, and then one. Create that one in your folder.
What is,
I'm listening.
yeah, no, never mind.
You sure?
So if the bottom number is, or if the top number is not X and the bottom number is just a number, it'll always just be like the first part of it, because it'll.
Because the dirt is a constant zero. Just create like a segment, that's all those 7 bits. Try this one. Last month, I maybe you'll have some for us.
That's what we do, that's right now.